Okay, going to look at the binomial distribution. We're going to do this in a couple of hits. This is sort of a background question, and then we'll look at what the real exam questions will look like. So this is based on Steve Adams. He used to play in the Thunder in Oklahoma, and I made up that 63% that he scores. I may have been really rude to him there, and I'm sorry, Steve, because you're a big frightening guy if I was. But the problem we're going to look at is if he takes three shots, what's the chance he gets them all in? We'll assume the shots are independent. We'll talk about this more, but that means, if we say that means we can find the individual probabilities and just multiply them together. I'll just uncover the answer here. There's nothing radical happening here. 0.63 first shot, 0.63 second, 0.63 third. Multiply them all together or cube them, and you get 0.2500. We generally go to 4 decimal places. And so that's there. If he takes 4 shots, what's the probability he gets exactly 3 in? And this is where we've got a couple of things that we know. We know the probability to get them in. We're assuming that is true. If we assume that is true, we're assuming that the probability he misses is the complement of that, and those two have to add to 1. So 3 in a row, then a miss. We can just use an extended version of what we did above. So 0.63, 63, 0.63, and then times 0.37. And we're at 9% chance of this happening. But taking 4 shots and getting exactly 3 in doesn't have to happen in this order. And in this big part of binomial distribution is dealing with the different orders. Here I've made a list, which is a laborious approach that we will hardly ever do. But those are the 4 different ways that the shot could either go in or miss. And so it's a binomial, meaning there's 2 options. So now I change it slightly and I get this slightly fancy form. The 4 is for these. Okay, 4 different orders. The 0.63 to the power of 3 are the 3 shots going in, and the 0.37 to the power of 1 is the 1 shot not going in. It's important that the 3 plus the 1 have to add to 4 because there's 4 shots. So the answer is made up of those 3 different parts, and that's why I've gone fairly heavily into the color coding there. So, and although this will be covered by your calculator and sort of invisible, it's important to keep that in mind. So the 2 key parameters that sort of describe any problem are the number of attempts and the probability of success. Now, on the formula sheet, we get this fancy formula here. I think Steve might have a couple of P's. I don't know. I'll just try that. This formula, and it makes it look more complicated than it is, but we will just, the pi to the power of r, pi is another notation for the probability of success. So in our case, the pi would be the 0.63. 1 minus pi, that part, is equating to our 0.37. Okay, and 1 minus 0.63 does give you 0.37. That's the whole point. And the powers will add to however many shots there are. We've got that weird notation here again, x standing to the full distribution of what can happen if Steve's taken a few shots, and the little x is referring to the actual number that go in. I think that time should be up there. I'm looking at that and thinking it's in the wrong place. Now, the whole listing thing here we can do in 2 ways. There is an NCR button on our calculator. If we go run option probability, then NCR, we can get it as an individual number. So how many orders could we have? 3 wet days out of a week out of 7? That would be 7C3. If we put it on, we get 35 different ways. This one up here, that is 4C3. Now, how that formula works, curiously, is not part of the course at the moment, so we don't have to worry deeper than that. this formula here is the formula that is given to you, but in the next clip we're going to look at how to deal with that using a calculator. So we'll stop there for this one.